Hi, welcome back to the lecture 1. This is module 2 of lecture 1. In module 1, we finished in this slide talking about a science of politics. What was political science? How could it be a science? In module 2, we're going to move to some more concrete ideas about theories and hypotheses. Okay, so we're going to move from our discussion of description about how the world looks like to actual causal explanation. So to do that, we're going to construct models or theories to explain patterns we observe in the real world. A model here is a simplification of the real world. It's designed to provide a simplified snapshot of reality. So, for instance, if you build a model plane or a model boat or some Legos or whatever, right, you're not including every possible nuance of the actual object. You're simplifying it down to a recognizable model. That's what a model building is, and that's what we want to do here. We want to take some really complicated causal relationship in the real world and boil it down to its essence, that we can examine a small number of causal relationships. We're going to be doing a lot more models as we go on, but here we just want to discuss what a model is and how it relates to theories. So the model is going to provide, as the theory does, an explanation of some causal relationships, and it's going to be composed of interrelated concepts. The theory here, which the model captures, asks the questions, what causes something and why? As I said, this theory is a series of interconnected statements that identify what causes something and why, right? How or why does A cause B? Here there are two components, the A and the B, or the X and the Y. Y is the dependent variable. Right? B or Y here is the dependent variable. It's the thing we're trying to explain. It's the something being caused, right? It's an effect, it's an outcome. In the examples I gave before, it might have been voting turnout or the poverty rate. Right? These are outcomes, these are effects, these are the things we're trying to explain. They're the things that are dependent on other stuff. The independent variable or variables are the variables that are meant to explain the dependent variable. Right? The suspected cause of the variation in our dependent variable. We often abbreviate dependent variables as DV and independent variables as IV or IDV, depending on where you look. These causal theories provide a story about how and why changes in the value of one concept influence the values of another concept. They should also offer additional implications or hypotheses beyond just this single hypothesis. That is to say, if your hypothesis is X causes Y, then we don't want the whole theory just to be X causes Y. The theory should be a broader enterprise than just X causes Y. And I'll go into why that's important very shortly. Right now, in fact. So there are different ways to develop theories. Two of the most important ones in the social sciences are deduction and induction. Deduction here starts with a theory and then leads to testing. Typically for deductive theory, we start with a bunch of assumptions about the way the world works. People want this or that. A very common one in political science is that people in power, people in office, want to be reelected. So they do things to get themselves reelected. Once we have those assumptions, we then deduce consequences from the assumptions. That's our theory, right? It's a connection between the assumptions and the consequences and the effects. Once we have those hypotheses that are the consequences of our theory, we test them empirically. That's a deductive process, and it's probably the most common one you see in political science for various historical reasons we'll get to a little bit later. Another way of deriving theory that's also very common is induction. Here we observe patterns in the real world. From those patterns, we induce a theory, we sort of infer a theory about how the world works from the patterns we see. We construct that theory from the observed patterns, and then from that theory constructed and its associated hypotheses, we then test those hypotheses on different data. Key to this induction process is that we can't just test a theory developed from the original pattern on the pattern itself. That wouldn't work very well for hopefully clear reasons, right? If we did that, then how would we know that our theory wasn't true just because it was formed from the pattern we're testing it on. Right? If I draw a picture and then I trace the picture, right, on some tracing paper, the fact that my tracing is very close to the original picture should not really impress us, right? I mean, I guess it's impressive that I could trace it, but in general, it's not a larger statement about the real world. It's a statement about how well we matched the particular picture. If we're creating a theory from a particular observational pattern, it shouldn't really impress us that we matched the pattern well. Rather, we want to derive additional implications of the theory we derive from the pattern and test them on other data. If our theory is to be believed, is to be supported, to have good support, then our implications we derived from the theory should also bear out on other data. That's important. Often political science tends not to put a lot of weight in induction, but induction is a completely valid and very commonly used way of scientific theory building. And in practice, a lot of what people do without really thinking about it is induction. We see things, patterns we think make sense to us. Often you'll see them referred to as stylized facts in literature. And then we build theory from those stylized facts, from those patterns we observe, and then test the theory elsewhere. Either deduction or induction are both fine. They're both things we can use to develop theory. Okay. So again, theory is the big broad thing connecting all the different concepts together and explaining how they all relate causally. A hypothesis is a more concrete expectation about what we will observe. Specifically, it's a statement derived from our theory that describes the expected covariation between the values of two or more concepts. A positive relationship is one in which the two variables move together. So x and y both increase, or x and y both decrease. A negative relationship is one in which x and y move in opposite directions. Either x increases while y decreases, or x decreases while y increases. Positive and negative relationships are both types of hypotheses, because a hypothesis is just a testable proposition linking two or more variables. So one hypothesis might be, as x increases, y should also increase. That's a positive relationship it's positing. Or a hypothesis could be, as x increases, y decreases. That posits a negative relationship. The important point is these hypotheses are testable and falsifiable. If I run some empirical test of the kind we'll discuss later in this course, and I see that increasing x does not increase y, I've falsified my hypothesis that x does increase y. And that's key. We're going to want to form hypotheses that are always testable and therefore falsifiable. The more concrete our hypothesis is, the more easy it is to actually falsify it, which is good, right? If I said y equals x squared plus 3, that's a very concrete relationship between y and x. That says y changes with x in an explicit way. That's relatively easy to falsify if I took data that did not show that relationship at all. Right? However, if I have a vaguer relationship, a vaguer hypothesis like x and y are correlated, right? That's still a hypothesis. I'm saying they change together, but I'm not really saying anything about how they change. That's much harder to falsify because the only thing that actually falsifies that is they have no relationship at all. So in general, more explicit hypotheses are easier to rule out and to reject. All that said, in most of the social sciences, we're going to focus on a particular type of hypothesis testing, which involves the null hypothesis. The null hypothesis is the hypothesis or the expectation of no relationship between the two concepts. So x and y here are varying randomly or do not change in value. So a change in x does not lead to any expected change in y. That's a null hypothesis. A null hypothesis is implied by every research hypothesis. Right? Every time I say a change in x leads to a change in y, as part of my research hypothesis, I imply a null hypothesis, which is that x and y don't vary together at all. The statistical testing we're doing in this course relies upon rejection of the null hypothesis. That is to say, if we can reject the null, that provides additional support for the research hypothesis. Right? So the goal of most of what we're doing is going to boil down to just this last bullet point. We're we're going to come up with statistical methods to see whether or not we can reject the null hypothesis. To see if we can reject the hypothesis that there is no relationship between our independent variable and our dependent variable. If we can't reject it, we're going to say we failed to reject the null, and we're not going to gain additional support for our theory. In contrast, if we do reject the null, we're going to say that we reject the null hypothesis of no relationship, and that provides support for our particular hypothesis of a relationship. It doesn't prove it or anything else, as we'll discuss in 1 second, but it provides support for that research hypothesis that there is a relationship between X and Y. Okay. Getting back to falsifiability in this context, right, it must be possible in principle to collect and evaluate evidence that permits us to demonstrate the hypothesis is not consistent with the evidence. A good theory here must be falsifiable in this way. It must produce testable, falsifiable hypotheses. Even if we can't test them at this moment, that's okay. There are all sorts of theories that have been put forth in all sorts of sciences in the world in which we could not test the theories fully until much, much later. Okay? General relativity was created as a theory over 100 years ago. Just in the past few years have we actually been able to test some of the theory's implications, some of its hypotheses involving gravitational waves. That's fine. As long as we can conceptually falsify our hypotheses, they're good hypotheses. But if we can't falsify them, if our hypotheses are like ice cream is good, we can't falsify that, so it's not a good hypothesis. It might be a perfectly fine normative statement about how we like the world to be, but it's not a statement about how the world is right now in a way we can falsify. So that's the key here, is falsifiability. If the data permit us to reject the null hypothesis, then we can infer the hypothesis is not yet wrong. That implies we can continue to use the theory in the future. That also implies that theory is provisional always, right? Future evidence might lead us to accept the null hypothesis and therefore reject our theory. Put another way, there's no number of tests that suddenly make us think, okay, we're done, the theory passes, it's proven, we never look at it again. All theories are provisional, all science is incremental. Importantly, that is not to say that all of our statements of theory are worthless. All of them help us understand how the world is given what we know now. The fact that in some contexts our theory might be falsified does not necessarily mean it's worthless in all contexts. It might just mean there's more nuance out there we have to figure out. Going back to gravity again, right? Newtonian physics and gravity works in a lot of contexts perfectly fine. However, there are contexts it does not work perfectly well in, and for those contexts we come up with more nuanced, in some cases more complex theories like general relativity. That's okay. It doesn't mean we throw out all of Newtonian physics. We don't stop teaching it in high schools. We don't in colleges. We don't stop using it to try to figure out how balls roll down planks and inclines, right? It's still useful. Just because we falsified it in some contexts does not mean it's worthless in all contexts. The same thing is true for political science. We're trying to capture very complicated interactions. We can't just discard the ones that don't work out right. Okay. So we do discard the ones that don't work out right. We don't discard them completely. Instead, we discard the pieces that don't work and try to modify the pieces that do to incorporate a wider range of understanding. Again, incrementalism is key here. It's important and should not be sort of looked down upon. Okay. How do we test these things? Well, we test them via operationalization, measurement. Now that word, it took me like a decade to pronounce that word. I still mess up sometimes. But the idea is to test any hypothesis, we must measure the concepts inherent in the hypothesis. So for instance, we talked before about education and turnout, and voting turnout. We have to measure turnout and education too. Some of these things might be easy to measure. Like turnout usually can just measure whether or not the people voted. Even there, you might ask yourself, is it the actual voting that matters, or is it people's statement about how they voted? If it's actual voting that matters, then the fact that it's secret tends to make things difficult. You can get information on actual turnout in many cases, but not necessarily turnout correlated with on the individual level, with all the individual level characteristics. So we often rely upon self-reported turnout, which is biases because people like to say they turned out to vote more than they did on average. So, but even then, turnout as a whole is a clearer concept leading to clear measurement, clearer operationalization. In contrast, education is a much more fraught concept. How do you measure education? Is it years in school? Is it level of schooling? Is it knowledge you have? There's all different ways of measuring it. Knowledge itself has all different ways of measuring it. You can measure by your answers to a battery of survey questions about the political world, or maybe something more complex or simpler. There are all different ways to measure things. Measurement, however, is necessary because that allows us to examine our data and evaluate covariation in our concepts and thereby test our hypotheses. To measure, to operationalize, we need to first come up with an abstract definition of our concept so we know what we're going for, what we're trying to get at. So education here, we're trying to go for concepts of individuals' ability to reason and think, potentially. If we weren't, we might use knowledge instead because that's information that might be relevant. Second, we produce an operational definition, right? A set of instructions that help us describe how to measure the value of that concept. That's very important to provide a clear and concrete set of instructions that people can use themselves, right? So, for instance, if I want to measure the concept of education, I need to be able to inform others how I measured it so they can repeat and verify my own measurement on, say, my own data or other data to see if my sort of statements are repeatable and replicable and hold up in more context than the ones I measured them in. That's important. Okay. How do, in general, I evaluate all these different operational indicators, all these different measurements, given that there's many different ways of measuring everything? Well, there's assorted ways of doing that. No one way holds sway completely. Validity is an important one, right? Does my measurement match my concept well or poorly? The more my measurement matches my concept, the more valid it is, right? So if my concept is turnout, then the probably most valid way of getting that is to actually find out who turned out to vote and match it to other characteristics of that person. Less useful ones might be ones that go further afield, like self-reported turnout might be less valid because of the inherent bias in asking people how they voted. You might also look at proxies that are much reserved from turnout, right? But you at home the day of the election, right? That's probably correlated with whether or not you voted, because if you're home all day, you probably didn't vote unless it was by mail, right? But it's not very well correlated probably. There's probably lots of reasons you could have left your house that didn't involve voting, so it's going to be a much poorer, much less valid measure of turnout. That's one. A second way of evaluating these measurements is reliability. Can I repeat this measurement and get the same value every time? Right? That doesn't mean it's not a biased value, but it means it's steady and reliable. Right? If I'm going to measure my air and my gas in my tire pressure, right? If I'm going to measure my tire pressure and I get different numbers every time, it's not a very useful measuring device. That's different from validity, which would say maybe I'm 10 psi off in my measurement, but if it's true every single time, I'm reliably 10 psi off every single time, right? I have a biased but reliable measurement. It might not be valid, but it is very reliable. Reliability is important because even if it's not necessarily accurate, I can do it every time. I can tell other people to do it the same way, and they can also do it, and thereby what I'm getting is clear, right? It's not relying upon just random chance. It's a clear measurement, and it means something every time I do it. Okay. That said, all measurement has error, right? All measurement is not perfectly valid, and all measurement is not perfectly reliable. There are two types of error that we deal with here. One is systematic. Systematic error is like bias. It's the tendency to assign values that are either too high or too low every time. Or they're too high or too low associated with some other variable. Random error is actually easier to deal with in a lot of cases. Always better. Random error, there's an equal likelihood of assigning a too high or too low value. So there's some random noise associated with the measurement that prevents us from actually getting at the truth. Okay, so sort of closing up this particular module, the goal overall is to build models, right? So first we're going to identify a question or a puzzle. We're going to then identify the dependent variable in that question or puzzle. We're going to propose a causal explanation or theory that helps us understand how that dependent variable changes with other things. We're going to identify the independent variables, which are our proposed causal explanations for how the dependent variable changes. We're then going to state a series of concrete hypotheses about how each independent variable affects the dependent variable. We will then identify null hypotheses for every hypothesis, right? So for every x that's supposed to change a y, we will have a null hypothesis that says x does not change y. We will then operationalize all these concepts. So we'll figure out how we're going to measure all of our variables. We will then collect data. We'll then test these hypotheses, and then eventually reevaluate our theory based on our results. If we find support for our hypotheses, we will feel our theory has additional support and feel more confident in our theory, even if it's not proven for sure. If our null hypothesis was not rejected, then we might not find support for our theory and maybe reduce our beliefs about the theory's accuracy and feel less confident in our theory and use it less often. This right here, this slide, it really sets out most of what we're doing in political science or all sorts of sciences. Most of the time we're going to spend this class past the first lecture is actually going to be on that 6th bullet point, the testing hypothesis, right? That's the only one that actually involves math, honestly. All the rest of these are theoretical, conceptual, right? We have to think of questions and puzzles and dependent variables and independent variables and theories and hypotheses, right? These are things that involve our careful thought, and they're by far the most important part of the research endeavor, right? No matter how well you measure, no matter how well you test, if you have no clear idea what you're doing, garbage in, garbage out. You just never can really be sure what's going on. So for this lecture one, we're going to focus a lot on these first few and also measurement. The part people often have the most trouble with, though, is that fifth part, testing, because the testing involves a bunch of math, and people who haven't had a lot of math before, that can be difficult or stressful for them. That's why we'll spend most of the last 3 lectures going through this methodically, assuming no real background beforehand in hypothesis testing and in statistics. But that said, it's important to remember that the most important things, the most important aspects of your development of research are those first bullet points, the ones before the testing, where you set up your theories and your hypotheses and your research design and try to figure out how to actually go about understanding the world better. Okay. So I'm going to conclude here with one example of all this, and it's about voter turnout again. So the question here was, why do some people vote and not others, right? We put forth a causal theory for that. So the earlier theory was very much like a hypothesis, right? Just education leads to more turnout. That's kind of like a hypothesis. Let's develop a broader theory for how this all works. This theory, which is not the only theory, it's just one theory, says that education exposes people to more information. This exposure to information increases one's awareness of problems. That awareness increases the likelihood that someone votes. So it's very clearly connected, right? Education gives more information. Information increases awareness to problems. Awareness makes you want to vote. It's a clear causal chain. Our hypothesis from that is the one we had before. The more education a person has, the more likely she is to vote. That is not the only hypothesis we could have drawn from this causal theory, right? We could have drawn hypotheses about information and awareness and figured out ways to measure information and awareness and try to see whether or not education did lead to more information and whether information did lead to more awareness. We're not going to do that here. We're proposing one single hypothesis in this particular example, that the more education someone has, the more likely they are to vote. So when we have our hypothesis, we draw a null hypothesis, which is there's no relationship at all. The amount of education a person has nothing to do with the likelihood that she votes. That's a perfectly fine null hypothesis. It says there's no relationship. That's always the null. If someone asks you what the null hypothesis is, it's always nothing's happening. There's no connection. Okay. Once we do that, then we're going to measure things. We want to have operational indices for the x and the y, the independent variable and the dependent variable. In this case, education and vote. Here, the vote, the Y, will be a 0 if a person did not vote, the most recent election, and a 1 if the person did. In practice, whether to specify what kind of election it was and so on, and whether or not self-reported or actual, but let's just keep it this way for now. The point is we're going to have a way to measure our vote. That's the dependent variable. For the independent variable, we're going to measure education. And here we're going to operationalize education as the highest grade the person completed. Again, that's only one way of measuring education, but that is a way of measuring education, and that completes our specification of those first bullet points. We have a question, a research question, a theory that causally connects our different concepts, a hypothesis drawn from that theory, a related null hypothesis, and then operationalization, ways to measure all of our concepts in our hypothesis so we can test it. And that's the setup. Okay, that's it. Next time we're going to talk more about theory building and how we get theories in political science.